section, I will focus on some main lathe types and some operations. Actually, we discussed some of them, but we will be going them once again briefly. And I said at the beginning that lathes are actually one of the most primitive, oldest type of machine tools we used throughout the history. Even we were using them before Christ. And the first type was actually the engine lathes. And since they were using kind of a large engine, and they were transferring this motion with the help of pulleys and some other gearboxes, that's why actually it was called as engine lathe. But after around to the late of 1800s or 19th century, we have separate electric motors actually installed on the lathe machines. And as you see, we have the similar topics. The components of lathes are written here. I already gone through most of them, but I would like to spend some time maybe on specific topics. For instance, the first one is about the bed, and you see that we have second type of beds and lathes. The first one, engine lathes. Now it's written that we have another one, gap bed lathe. What is that? With the help of them, we can have large particles, actually large workpieces mounted on our lathe. Assume that this is actually your lathe. If this is a configuration, that will be the maximum workpiece you can handle. But if you do remove this part, or maybe at least remove some portion of it, then you will have such a lathe machine. And with the help of it now, you can handle much larger workpieces. And this is called as gap bed lathe. And some companies actually are using such type of lathes, but not as very common with respect to the conventional type of lathes. If in your company you want to machine actually larger cylindrical parts, then that might be a good option. And for the carriage, we discussed all these issues. And for the headstock, this is the things actually we discussed. But for the tailstock, I may mention that. We will see probably some images and some things in our video that onto the tailstock, you can even install some tools. So once you install some tools on the tailstock, let me draw a top view. Assume that this is your headstock. You have your workpiece rotating, and assume that these are some rays of your tailstock. And on this tailstock, this is tailstock, and this is headstock. You may have some specific cutting tools. For instance, you may have a drill or a boring tool, and then if you may move it in this x-axis and try to machine your workpiece. So it's possible also with tailstock. And if you remember, I said also that for longer, thin and slender cylindrical parts, you may hold it from your tailstock and also from obviously spindle. With the help of it, they will be much more stable. You can decrease the amount of vibration, bending. You will have no bending. But if it's too long again, you may have some rest, and these rests might be follow rest or a steady rest. They are just used to make such longer parts as stable as possible. And we have feed rods and lead screw, as I said. If you want to have a controlled motion between the spindle and your carriage, then you need to use lead screw. And how do we use it? We simply close the nut around our lead screw so that the carriage will move with the motion of our lead screw. So if that's the case, you can easily open screws, threads on the outer or internal surface of your workpiece. Now, how do we specify the lathe? So what are the main dimensions we can talk about? There are three of them. And the first one is the swing. It's actually, let me again draw a kind of a typical lathe here, a very simplified version. Again, this is our head, this is tail. Now let's focus on what is swing. Swing is actually the maximum diameter we can handle on this machine. So this is a workpiece, and as you see, we can handle it on this machine. and swing is actually the diameter of this workpiece. Then we have other dimensions which are specifying the lathes. Other one is maximum distance between the headstock and the tailstock center. So if this is the center of the tailstock, and if this is the center of headstock, then that is the dimension actually the second item is referring to. And the last one is the overall length of the bed. It has this dimension. So with 3 dimensions, we can somehow specify the lathes. Now I will focus a little bit on work holding or workpiece holding device and some accessorizers. The first one is, as we discussed, is a chuck, the most popular one, the most frequently used one. And in some chucks, we may have 3 jobs. If this is the case, then probably they are mostly self-centered. They have most self-centering capability, which means that if you simply rotate a kind of a screw, then all these jobs will actually move and you will be squeezing your workpiece. We know that we are using cylindrical part. Assume that you have a 3-job chuck. That is the kind of a chuck you have. And with the help of a kind of an screw here, what you do, you rotate this screw, and then these chucks will be, jobs will be moving into the workpiece, and then they will fix that workpiece into the spindle. And instead of 3-job chucks, we may also use 4-job chucks. The fundamentals are the same. They may be self-centering, but for most of the time, we prefer to use them independently, so that you can handle maybe square parts, some irregular shapes can easily be handled compared to the 3-job chucks. And if you actually actuate these type of chucks with electrical, pneumatic, or hydraulic powers, then they are simply called as power chucks, but the fundamentals are the same, their aim is the same. They are trying to hold these workpiece firmly, so that during this high speeds, we will be always keeping our workpiece in place. And then we have other types of work holding accessories, devices. Other type is called as collet. These are some examples of collets, by the way, these 3. And we have 2 types of collets. The first one is actually draw-in type of collet, or we sometimes call it as pull type of collet. And we have push-out type of collet. And this is the second type. The C is an example of an push-out type, but A and B are examples of draw-in or pull type of collets. So what is a collet, by the way? It's, as you see, a longitudinal split tapered bushing, which means that we have, let me draw a kind of an collet here. They are obviously cylindrical in shape. They have obviously some hole at the center, since we will be putting our workpieces inside this collet. And the thing is that they have such openings until maybe here, another opening here, the same opening. So they are quite flexible at the top region, so that you can easily put your workpiece inside, like this one. And then if it's an drawing collet, what we do, we push this collet inside this case, and then since these parts will be CQs, and then the face of our collets will actually cover the surface of our workpiece. So if you look from the top, assume that this is your workpiece, and then what will happen? The face of our collets actually will secure this workpiece from all the periphery of the workpiece. So we can say that the contact between the collet and the workpiece is much more compared to the contact between the chucks and the workpiece. And we mostly use this type of work holding devices for very smaller parts, maybe maximum 25 millimeters, but we prefer to use them for smaller diameters. And on the other hand, we also have the second type. This one is called as push-out type of collet. The fundamentals are the same this time. As you see, we put again our workpiece into this collet, and then what we do, you can see these screws here. We rotate it, and then once you rotate and move that actually spindle into that overall hood, then this part will be secured, and again the three parts of your collet will be securing the workpiece inside. But the rest is the same, just the direction of motion is different with respect to the first case. Then we have face plates. These face plates are actually for irregularly shaped workpieces. We can see an example here, although this is a cylindrical shape, but the thing is that they have many independent moving items there, and by adjusting them properly, you can easily handle very complicated shapes and have no problem while you are rotating them at high speeds. Then we have another example is as a mandrels. We see some three mandrel types here. The thing actually at the center is mandrels. So you can use mandrels only if you have some actually holes at the center of your workpiece. So you can assume that this pan is the mandrel, and then these will be rotating these workpiece, and then you can do machining. So we have, as you see, three types in the solid mandrel. This is a simple type, and we mostly use tapered type of mandrels so that we will push them to the tapered region, and it will not slide away. It will be fixed to that point. And then what we do, we bring our cutting tool and remove material from the side surfaces and also ends and faces. This is possible with the solid mandrel type, but if you are using gang mandrel, then you can only machine from the side surfaces. The idea is the same, but the advantage is that you can machine many of them at the same time. So I can have, let's say, two of these workpieces, and with a single movement, I can machine the side surfaces of these workpieces. But the problem is that I cannot do machining on the end faces. Since it's closed, our tool cannot go inside. So we can say that this is a disadvantage of gang mandrel, but we gain time during the machining. Then we have cone mandrel. It's somehow similar to the solid mandrel. The difference is that, as you see, we have a conic tapered surface on the mandrel. The advantage is that it can easily fix different size of workpieces, since it has a tapered surface here. Even though you have a larger workpiece, a larger hole, with the help of this tapered surface, you can handle various sizes of workpieces. Furthermore, we can have special accessories, but these depend on obviously on the company. You may design your own work holding device, but the ones we discussed are the most popular ones used in machining operations. Now let's briefly talk about lathe operation. Actually, we already did, so I will simply talk about the long and slender parts once more. While I was discussing the components of the lathe, I said that if you have long parts, then you should be holding them in between the centers. We have one center on the headstock, one center on the tailstock, so we put our workpiece in between these centers, and then if it's too long, slender, and what we do, we have some extra rest underneath. And if this rest is not moving, it's called steady. If it's moving, then we call it as follow rest, and they are all moving on the race of our lathe machine. And with the help of them, we can machine such longer workpieces easily without having any instability and vibrations, chatter. These will be eliminated. Since we already discussed these, I'm not going to spend time. As I mentioned, we will have special sections on boring, drilling, reaming, and you will see in upcoming sections. Now let's talk about some types of lathes. The first one is one of the simplest and the smallest ones. They are called as bench lathes. You can simply put them on your desk and do machining. But obviously, these are only suitable for machining very soft materials, plastics, wood, or maybe aluminum, but obviously not for steel or other harder materials. And they are mostly manual, but we may have also some low power versions. And if the dimensional accuracy of these bench lathes are higher, then we call them usually as tool room bench lathes. And with the help of them, we can machine little products, but the accuracy of them will be very good. Then we can produce any special machine depending on your resulting product. For instance, if you are machining railroad wheels, then as you know, they are huge, quite huge, so you need to design a special lathe machine for them. Otherwise, the lathe machines you in your company probably will not be able to do machining on these. Then we have tracer lathes. This is something different. Let me try to illustrate it. So in these actual tracer lathes, as the name implies, the lathe traces a kind of a template. So what you do, you provide a kind of a template here, and then if this is your workpiece to be machined, your cutting tool actually, if this is your cutting tool, it will follow this motion here. So we have a kind of a mechanism here, so that while moving to right, this is not cutting, by the way, it is following simply the profile. While this one is following the profile, it transfers this motion to your cutting tool, and then this cutting tool will be doing forming operation, doing turning operation on the workpiece. And this is called as tracer lathe. It's very similar to duplicating, for instance, the keys, if you have ever seen that. But these days, we are not using such tracer lathes anymore. Instead, we now have CNC type of lathes. And instead of giving a template, what we do, we provide instructions to the machine, and then the machine will follow these instructions and have such complicated profiles on the workpieces. Then we have some automatic type of lathes. Why they are called as automatic? Since let me again illustrate it. At the beginning, we said that we have a spindle, and this spindle is responsible for holding the workpiece. And in order to mount your chuck into that spindle, you need to have an opening at the center of the spindle. Okay, this is a spindle. We have an opening at the center, and now assume that this is part of your chuck. And then what we do, if you have, if you are producing very, let's say, maybe parts similar to this one, then your length is not too much, and what you are going to do, you will be feeding the workpiece continuously through this opening, and then your cutting tool will perform some motion on it and then cut it out. This will be done, and then what we are going to do, we will be feeding this workpiece, long workpiece, once again, and then do the same operation on the new part of the workpiece. So that's why it's called as automatic type of lathes. We have fully versions, semi-automatic versions, but obviously in the fully one, we don't need to spend too much time on handling the chuck, handling the workpiece. But in the semi-automatic versions, you may need to collect the finished parts and maybe feed your workpiece again into the spindle. And if you don't have tailstock, since in this one we don't need to have a tailstock, these machines may be simply called as chucking machines or simply chuckers. Then we have another type of lathes. They are called as automatic bar machines, very similar to the previous one, but the difference is that they have much more capabilities. They are not simply doing turning, but they can do threading, cutting off, taper turning, other various drilling even can be performed on these machines. And we have two types of them: single spindle automatic bar machines and multiple spindle automatic bar machines. In the single spindle version, as the name implies, we have a single spindle. The part is rotating again, and the thing is that we have many tools. We have one tool underneath, one tool above, on the side, and at the end face. So they are doing operation at the same time while while your workpiece is rotating, and that's why they are called as Swiss type, automatic type of bar machines. We do many operations on the same workpiece at the same time. Then in the second version, it's very similar, but the difference is that we have multiple spindles, so there might be 3, 4, 6 spindles on your main spindle. With the help of them, obviously, we can machine many parts at the same time and decrease your overall manufacturing. Then we have turret plates. Let me show them on a sketch. Yes, these are some examples of, this is an example of a turret plate. The turrets are actually here. And what do we have on a turret? There's a square turret. Let me draw it. It's a square turret. What we have 4 tools on each actually face. So what we do is simply rotate it and then approach it to our workpiece and do the machining. And even more, sometimes we may have a specific ram. It may be moving on the roads, and on that ram we may have again a square turret or a hexagon turret. Obviously, if it's hexagon, we have 6 different type of tools. And again, by moving your ram over your workpiece, you can start the machining process with different tools. And furthermore, considering the tools, actually, as you see, the advantage of this turret type of place is that you have many types of cutting tools installed on the machine. You don't need to spend time on installing a new cutting tool. What do? You simply rotate your turret and start a different turning operation. But these days, in most of CNC lathes, instead of doing it manually, we have automatic type of tool changers. They're abbreviated as ATCs, and I have an example here. This is, for instance, a kind of a magazine, and we have many cutting tools on it. It may be performing drilling operation, turning operation, boring, reaming. As you see, we have several cutting tools responsible for different operations. And with the help of automated system, once you write proper instructions, then your machine will take the right tool for it and then install that tool into the tool holder and do the machining. This time we don't have a turret, but instead we have a magazine. Your equipment, actually, your tool holder moves to that place, grabs, let's say, reamer tool, and then moves to the machining region again and do the machining. So this is the way, actually, these days we are using the lathes, CNC lathes. And on this table, you can see some roughness values of different operations. For instance, if it's a rough cutting operation, obviously we have high surface roughness values around 50 to 25 micrometer. And if you do casting, depending on the type of casting, you may have this much roughness. But obviously, if you do finishing operations, we haven't discussed these, but if it's a finishing operation, then that means the surface roughness value of your resulting part should be lower, maybe less than a micrometer. But if you do some turning operation, you see, depending on the type of turning, you may have surface roughness of 25 micrometer or less than 50 micrometer. It depends on the type of cutting tools you are using and depends on the capabilities of your machines. And then if you remember, such turning machines, such lathes should have some chip collection systems. In the image I discussed, we had a chip pen, but we may have some more complicated versions, and especially CNC type of lathes. With the help of them, we can easily handle all these chips, put them into some kind of bins, and then try to recycle our chips. And here we have a similar plot with very similar to the results in this table. It's showing actually tolerances in terms of different operations. For instance, if you are producing, if you are machining a workpiece having a diameter of, let's say, 20. So if I draw such a line here and you look at it here, the y-axis, if you do the machining with drilling operation or rough turning, that will be the tolerances you are going to have at the end of the operation. It's about 3 millimeter, which is very high. But if you do honing or lapping like finishing operations, then you will have less tolerances, maybe less than 200 micrometers. So obviously, if you are doing finishing, semi-finishing like these, you'll have less tolerances. But if you do rough machining or other machining operations, you'll have high tolerance values. And now let's see machine actually threads by using the lathe machine. This screw threads are highly important since in assemblies we always have threads inside our holes, or we have some tools, bolts, screws, and we need to open some threads on the external surface of these joining mechanical elements. The conventional actually manufacturing for such threads is actually thread rolling. We haven't seen now, but while we are discussing such forming operations, you'll see that in less than maybe a second by doing rolling, we can open the whole threads on an external surface. But we can even do them by machining operations on lathe machines. We have internal threading and external threading. They are all possible with the lathe machines. The point is that if you remember, I said that the relative motion between your carriage or the tool and the spindle speed is highly important, since it directly determines the thread of your threads, the lead of your threads, and it's actually the axial distance you are moving in one revolution. So that will define the main property of your threads. And we have different approaches to do the threading or thread opening. So you may be going directly into your thread, or you may be approaching it from side surface, or have some rough operation and then do maybe finishing operation on your threads. So you see this is the first cut, for instance, the depth of cut is not too much, or the number of threads are not so high, but then later after you do some cutting operation, you can do the last threading operation. This is how it is done, and you can obtain high quality threads on your lathe machine. And we said that we can even do internal threading, but you should be using the tool installed on your tailstock. You cannot do it with a tool installed on your tool post. Let me stop for now.